Good morning, everyone, and welcome to this 29th ETP4HPC webinar. I am Pascal, I'm ETP4HPC's Communication Manager, and my colleague Gabriela is also here to help run the show, especially to help me with the questions. So for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC, and we are a private member of the EuroHPC JU. And today we are going to take you on a trip to the Czech Republic to visit Karolina. But before we delve into today's subject, I would like to share a couple of practical information. So this webinar is recorded and you will receive the link to the recording. This webinar is in listen-only mode, but you can ask questions. You can also see the chat. And you can see the list of attendees and you can download handouts. And today the slides are available as a handout. So if you go to the handout section, that's the one shown by the green arrow, you can download the slides and you'll have them already. Okay, so enough for practicalities. Let's welcome today's speaker, Dr. Branislav Jansík. He's the Director of the Supercomputing Services at IT4I, IT for Innovations. So welcome and thank you very much for accepting to be our speaker today. So without any further ado, we'll delve into today's agenda. Very simple. Branislav gives his talk and then we will take your questions at the end. Okay, so Branislav, I will hand over to you. Sorry, here we are.
Okay.
So now you should be able to share your slides.
I can share the slides now. Can you see my slides?
Not yet, but it's coming. Yes, now we can see your slides. Perfect.
Okay, perfect. And can you see also the pointer that I'm moving around?
Yes, I can see it.
Okay, that's very good. All right, so shall we start?
Yes, the floor is yours.
Okay, thank you very much. So everyone, welcome once again, and it's my privilege to introduce the Karolina system installed in Czech Republic, and also to speak a few words about the LUMI-Q ecosystem. My name is Branislav Jansík. I'm head of the Supercomputing Services here at IT for Innovations. My background is in electronic structure theory, material science, and computations. Okay, so let's focus now on Karolina system, and my talk will be rather technical. So if we will then take the questions towards the end. However, if there is something that is intolerably too much technical, or you really need to go to a question, I can, of course, in principle, take a question. Okay, so let's talk about the Karolina supercomputer. So this is the picture of the Karolina supercomputer on the computer room. The Karolina supercomputer was installed in 2021, if I remember correctly, with a full operation in 2022, and is a supercomputer installed by HPE. So this is a nice picture. It's a very powerful computer, and here is some overall numbers regarding the power. Basically, if I add up all together all the performance that we have in the Karolina supercomputer, I will arrive at about 15.5 petaflops in peak performance. And if I run LINPACK on these machines, and if I am allowed to add up all the LINPACK performance, it's over 9 petaflop in LINPACK performance. When we look at the performance at For example, for machine learning, at the lower precision, I will talk about it a little later, then this can amount up to 350 petaflops. The Karolina supercomputer is basically composed of several partitions that have different performances, but I will talk about that little in the next slide. When we installed the Karolina in 2021, it ranked as a number 69 on the top 500 list, and it ranked as number 19 in Europe. It is also a very green computer. It used to rank at about now number 15 worldwide on the green 500 list. So it was pretty big computer with a very good impact. However, this ranking, the number 69, that's just for one of the partitions. That's just for the accelerated partition. If we were able to run a hybrid LUMI-Q and add together the numbers for the individual partitions, we would probably rank somewhere below number 40 on the top 500 list. So it's a major computer operated in Czech Republic by ETP4HPC's National Supercomputing Center. It's maybe also important to mention that this computer has been procured in collaboration with the EuroHPC JU. So this machine is funded by 35% by the EuroHPC JU and is one of the petascale systems of the EuroHPC JU, accepting the workload also from the EuroHPC, and in this way accessible to the researchers, not only from Czech Republic, but across Europe. All right, let's go into detail. Now we'll go and look what is really inside of these boxes so that you have a detailed understanding of what we have and what the performances are and what the hardware is. Okay, so this picture shows a simplified picture of the Karolina supercomputer, simplified architecture. So what we see here is we have four partitions. We have a partition of which we call a universal partition, which consists of 720 CPU nodes. It's a regular non-accelerated CPU nodes, providing in total over 92,000 cores. So this is the universal partition. On top of that, we have an accelerated partition. The accelerated partition is nodes like this. It's a 72 nodes that are heavily GPU accelerated. So these nodes have 8 GPU accelerators each in them, and these are A100 GPUs. So in total, we have 576 GPUs in this GPU accelerated partition. On top of it, we have a data analytics node that is significant because it provides basically shared memory processing, and it provides you 24 terabytes of a shared memory. And in addition to this, we have a cloud partition. The cloud partition provides over 4,600 cores and 9 terabytes of RAM. This partition consists of basically 36 nodes that are of the same configuration as the universal partition, but they are connected together in a cloud and in a cloud environment. The service is provided via cloud environment. On all of these nodes are interconnected via InfiniBand HDR full FAT3 topology network, where we have basically we have the connections to the universal partition, also to the accelerated and all other partitions. The universal partition nodes are connected via the HDR 100, so there is 100 gigabit links to these universal nodes. When we look at the accelerated nodes, there is 4 times 200 gigabit accelerated link into every of these accelerated nodes. Then we have, I think, 2 times 200 gigabit links to the data analytics and so on. What is also very important is that these nodes across this network share a number of storages. Out of this is very important one is the scratch storage. So there is over 1 petabyte of a scratch storage. It's an all-flash storage parallel distributed file system, and it has there is 1.3 terabyte per second, up to 1.3 terabyte per second in aggregated read performance, a little less than that for a write performance. So there is a very powerful shared all-flash storage that is available to all these nodes. Then we of course have a number of login nodes, and other nodes. We have a home storage, we have an infrastructure and backup storages inside, and all of these nodes are connected via dedicated gateways into a project storage that is not part of the Karolina. It's an independent storage sitting on the computer room that provides another up to 15 petabytes storage, where you actually are supposed to store your project files and your intermediate data, your results, and so on. So this is the overall picture of the Karolina architecture, and now we can have a look in more detail what's going on and what's the configuration of all these individual partitions and what is special about them. So let's focus first on the universal partition. So the universal partition, these are basically some picture. It's a you can see it's a 720 nodes of this kind of HP ProLiant type server. These nodes are equipped with two sockets using AMD EPIC 7H12 processor, in total 2 times 64 cores on this. Each of these sockets, they are direct liquid cooled, so they are water cooled, so there is a water coming in and water coming out. It's a hot water providing the cooling. What you can also see is 8 memory channels on each of these sockets, which provides a very good performance. So in total, with these 8 memory channels, we have there up to 256 gigabytes of RAM memory, and the node is connected by a 100 gigabit link. It runs, I think still it's CentOS 7.9 at the moment, but we will be very shortly having an upgrade to CentOS the 8 series. In total, these 720 nodes provide over 3.8 petaflop in peak performance. When we look closer about the performance of these nodes, so these are very, very powerful nodes. When we look at what this EPIC is giving us, when we measure the performance, you can really expect, and these are really measured numbers, you can expect over 5.3 teraflop per node. So this is a peak performance that we have seen that these nodes can run and sustain using these two AMD EPIC processors. So that's the pure CPU power, that's the pure CPU performance. However, this is the one that we can see that can actually in practice be sustained on these nodes. Well, that's not the only metric. Another very important metric is of course the memory throughput. In addition to the processor performance, we have there with these 8 memory channels, we have there basically 32 gigabyte DIMMs providing about 25 gigabytes each. So we're having these 8 channels and so on, we gives us up to 256. Having these DIMMs gives us up to 256 gigabytes of RAM, and if everything is done correctly, we can get up to 200 gigabytes per second in a memory throughput. Because these are AMD EPIC processors, they consist of chiplets, so they have a very strong NUMA effect. There is a strong NUMA effect. You can see here the NUMA matrix. This basically is telling you the relations between the memory throughput that you can achieve locally on the individual NUMA node, on the individual chiplet. So this throughput would correspond to the maximum throughput that we can get on the chiplet, and then there is a slowdown if you go outside to the more distant chiplets. So there is a NUMA effect. There may be a slowdown. It is very important to respect this on these processors. It is important to use the techniques such as first touch and similar. And it is very important to get a good performance, to use proper pinning of your processes to the cores, so that they don't migrate once the memory is allocated to them. In that way, the NUMA effects can be significantly reduced. It's basically the same about the cloud partition. It's still the same configuration. The cloud partition is configured in the same way. We have the only difference is that there is a different software stack, and there are some local NVMe storages to support the cloud environment. What is most important and where the most of the performance comes from is actually the accelerated partition. So we have here 72 nodes. They have AMD EPYC processors, 2x64 cores, but that's not maybe so important. These processors are there primarily to drive the accelerator cards. And then there is 8 times NVIDIA A100 with 40 gigabytes of HBM2 memory on each of these cards. We have there 124 gigabytes of memory, of RAM memory on top of these processors. And these nodes is connected via 4 times 200 gigabit link, again running CentOS 7 at the moment, switching to CentOS 8. And this is where most of the performance of the computer comes from, over 11 petaflops in performance we have in these 72 nodes. These are very powerful nodes, and what is worth mentioning, there are several features of this. These 8 NVIDIA A100 cards that we have there, they are all connected, they are connected via NVLink network inside, but they are not connected peer-to-peer. They are connected via NV switch. And this is a very important feature. This feature basically allows us to get a full speed between any pair of the cards, full throughput across any pair of the cards, while all the other cards are also involved in the communication. So there is the switch here is making sure that we have no collision on this. We have no collisions on this network, and this can be used with great advantage to access from one card to access a data that is available on the another card, basically with a full speed of over 600 gigabytes per second. This can really be used when we use a unified the unified address space feature. So this is something that is provided by CUDA. You are probably aware of this. So basically, we have, if we look at the multiple memory address spaces, I have an address space for a CPU, address space for a GPU, and another different address space for GPU. Under normal conditions, the GPU number 1 cannot access the memory of the GPU number 2 and cannot dereference the pointers that are allocated on the GPU number 0 or the reference pointers that are allocated on the system memory. The NVIDIA driver, in combination with this technology here, with the NVLink and NV switch, is providing us a unified address space, a single address space, where all of these memories are interconnected via this NVLink, and they are accessible as a unified address space, so that we can basically we can access the memory freely from any of this hardware to any of this memory. So the CPU can see into the memory of GPUs, and the GPU can see with a very good throughput to the memory of other GPU or the CPU. If used well, one can really take advantage of the 40 gigabytes of the HBM2 memory that is installed on every of these accelerator cards that we have in the node. All right, these A100 cards that we have there, they are very powerful. These are A100 cards, NVIDIA. However, their power is not completely free lunch. The power is very, very high. However, to get to this power, one has to use, there are several prerequisites. Well, one of the most important is this power is hiding in FMA instructions. Fused multiply add instructions. A fused multiply add is basically when you have a 1 A times B plus C, and you can do all of this and return the result in a single instruction. So this is where the power comes from. Well, probably most importantly, the power actually comes from, traditionally it comes from these instructions. To really get the full performance of these A100 cards that we have, one has to use the VMMA instructions, which basically stands for warp matrix multiply add instructions. And these are basically a matrix operations. In a single instruction, you do a full matrix times a matrix plus a matrix, where the elements of this matrix are distributed over the threads running within a simple warp. And these A100 cards can do this not only in FP32 or FP16. These A100 cards can do these operations on FP64 operations. Please note that this is just an illustrative pictures. The matrices there are not 4x4. In fact, these would be actually for the FP16, they will be 16 by 16, or if we go to FP64, they will be 4x8 matrices. But one has to use these matrices, and when these matrices are used efficiently, one can actually get and sustain very close to a peak performance of these accelerator cards. However, to do this, you also really need to express large amounts of parallelism to get a flop performance in a traditional way. Basically, in these FMA instructions, one has to go to approximately 300,000 independent data streams. We have there 108 streaming multiprocessor. We want to overload them approximately 12 times. Then we want to use 32 threads per warp. And then we also need to respect the instruction latency and the pipeline length, which is approximately 8. So this is roughly the number of independent data streams, the volume of parallelization that you need to express to really use this card in full. This card also has a very good memory throughput. However, we also need a very large number of independent data streams, over 1 million data streams, or 1,300,000 data streams, to safely get a full throughput and to hide the latency. When everything is done well, the performance here is per card is 1.7 teraflop in FP64 in the traditional FMA instructions. And if you go to these tensor core instructions, this warp matrix multiply add instruction, we could really measure 19.5 teraflop in performance when you use the FP64. So it's a very powerful machine, but one has to use it wisely to get the performance out. So this is the performances that we were really able to get out of this machine. When using 8 times of these NVIDIAs, we were able to get over 77 teraflops per node, per accelerated node in FMA, or over 155 teraflops in warp matrix multiply add instructions. If you go to a reduced precision, you can go over 2.4 petaflop basically per card, which is insane throughput, and which is insane performance. The similar is with memory performance. When we do everything correct, we can get per card, we can get up to 1.3 terabyte per second, 1,300 gigabytes per second. If we combine all the cards, we can go over 10,000. When we go from card to card, there is of course significant penalty. This is really a measured NUMA matrix. You see, if I go 10 is basically the throughput that I get on the card. If I go to a different card, it can be approximately 4 times slower. However, it's very comfortable to use this unified address space, because one can basically from one card reference a pointer, so in the memory of the other card, and get the result still with very good performance, very good throughput. Okay, data analytics partition. If I go, we have this HP SuperDome Flex machine with over 24 terabytes of memory. This machine basically is combined like this. It's basically 32 Intel Xeon processor sockets, giving together 768 cores, and they are connected in all-to-all topology by an internal so-called NUMA network that is used to exchange data between these processors and to support a shared memory. So a user can really see a shared memory of 24 terabytes, and can see a single node basically with 768 very powerful Xeon cores, with a peak performance over 70 teraflop in this processor. However, one has to respect that this is a shared memory. At the same time, it's not the NUMA node. It's basically there is of course a strong NUMA effect, and the performance needs to be and this has to be respected. Okay, I think this is a slide about the performance of a single universal partition node, but I think we have gone through this already. If I go to a compute network, the network is composed of the InfiniBand. It's an InfiniBand HDR network in a non-blocking topology. The link speed is a 200 gigabit per second. However, we are connecting to these leaf switches. We are connecting the individual nodes, and the regular nodes are connected by a 100 gigabit link, but then the accelerated nodes are connected by multiple links. To this network is also connected a scratch storage, and this is an interesting one. It's basically a cluster store E1000 all-flash storage, which is very, very powerful. There is a 24 independent storage units, and then these storage units has these object storage targets that are all SSDs. We can get the throughputs over 1.3 gigabytes per second. I have 1.2 here, but it's actually more than that. What is very important is to respect is that this is a Lustre file system. It's a parallel distributed file system that is on which this is built on. So there is number of object storage targets, and the data are striped across these object storage targets. And for an optimal performance, you need to set the object storage targets, and you need to set the striping size and the striping count correctly for your application. We have the default. The default is very simple. We have I believe, one megabyte stripe size, and stripe count is 1, meaning that your files are not striped. They are all stored in a single object storage target. However, to get a full performance of the storage over a single file, you can or you can also set this for a directory. It is very good to set this stripe policy for your file as necessary, so that the files are striped across multiple storage units, across multiple object storage targets, so that you can fully utilize the parallel access and the parallel performance of the file system to access your data, especially if these data are stored in large files. Here are some data about how the storage is used. So basically, we provide a quota. Typically, by default, we provide a 20 terabyte. However, this is a scratch storage, so we delete the data that are older than, I believe, 90 days. You also, however, if you need more than 20 terabytes of it, it's of course possible up to a very large portion of the storage. Meaning that at the same time we will be pushing on removing this data once they can be really scratched, once they serve the purpose of the temporary storage. Okay, so the Karolina system is governed by the Slurm scheduler. So you interact with a Slurm to submit your jobs. We have been using PBS before. But we have switched to Slurm, as it turns out that this is what becomes a standard across Europe. All of our systems at IT4 Innovations are now using Slurm. When you start with Slurm on an unknown system, I really recommend to run a command sinfo or sinfo-s, and this will give you immediately an information about the queues and the basic configuration, what you can expect from the Slurm. We are using policies that are fair sharing and backfilling. Basically, what the Slurm will do is that it will try to all the jobs that are being submitted. It will try to make sure that every user over a defined period of time, which is approximately 2 weeks, can get approximately an equal amount of computations, meaning that the fair share will basically make sure that if you compute a lot over a period of time, then your priority is going down so that the other people can compute as well. And this is being kept in approximately 2-week window, and then of course your old history is getting less and less weight, and your priority goes up again. So this mechanism basically makes sure that it's not a first in, first out, and that on the contrary, if number of users put in their resources, then the ones that computed less will get increased the priorities until they can compute more, and then the priority goes down again. And whenever we have the priorities set up and the jobs scheduled, there still may be some empty spaces where additional jobs can be squeezed, and that's called the backfilling. That's basically, we then use all the remaining space are filled with lower priority jobs so that they can fit together, so that the computer is utilized well. All of this is in a very good detail described on our documentation pages. So once you are there, you can you can look what the status is. You can look at the SQ. You can also look at the extranet, where we have a dashboard where you can see what's going on, how the computer is utilized. You can even see, I'm sorry, this is not going to happen today, 17 o'clock, but you can also see the electricity status, the electricity stats, meaning you can see the power consumptions of your job that as has been measured via some internal counters. If you have a very large amount of jobs, and perhaps we have 128 cores on the machine. We have 8 GPUs. Maybe you don't want to use all 8 GPUs. Maybe you have 100,000 of jobs, but these jobs are relatively small. They can only use a fraction of a GPU or only few cores. We have a tool to schedule this very efficiently. This is not very good to do via Slurm, because Slurm can get really overloaded with this, and it can create other problems. It is very comfortable to manage this via a hyperqueue. So if you have a large amount of jobs, if you have a large amount of small jobs, only few cores per job are needed, or maybe only a fraction of GPU is needed. Maybe these jobs also have a complicated dependencies together. Then hyperqueue is an answer. There is a detailed documentation about it. Hyperqueue is basically a meta scheduler. It will take your large amount of small tasks and it will put them into an independent little scheduler that you control fully. And this scheduler will very nicely and transparently talk to the Slurm, and will allocate the nodes and will run your tasks as fast as possible through these nodes. This is really very good for any kind of hyperparameter search type of jobs, but not only that, even for any time whenever you have large amounts of jobs, especially with complicated dependencies. I mentioned that we have also a cloud partition. The cloud partition is operated or is accessible via the OpenStack in 2 variants. So there is an OpenStack interface. You can go to the OpenStack website at IT for Innovations, where every user has an opportunity to run the virtual machines. By default, you have some very small defaults set up. We can basically see these defaults here, and these defaults are available to anyone. So you can anytime set up your virtual machine and run it at Karolina cloud infrastructure. If you require a different configuration, or if you require more of these resources, they can be applied for, and then these limits can be modified individually as necessary per project. Okay, so we have this very impressive machine, Karolina. I wanted to spare a few words about how this machine is connected to the quantum machines and to the rest of the Europe. Well, basically, we are member of the LUMI consortium, and the LUMI consortium operates the LUMI supercomputer located in Kayani, which is one of the pre-exascale Euro HPC systems. And based on the LUMI consortium, we have constructed a LUMI-Q consortium aiming at quantum computers. The LUMI-Q consortium, on the footprint of a LUMI consortium, basically unites three different large computers: the LUMI computer, the Karolina computer, and also the new computer that is being installed in Poland, the Cyfronet in Krakow. The consortium brings together a lot of expertise, and it also brings in together also a number of other quantum computers, including one installed at VTT, the one installed in Chalmers, Göteborg, and another two installed in Netherlands. So this consortium, within this consortium, we put together the expertise, resources, and money to deploy a quantum computer here at Karolina, here at IT for Innovations, to integrate it with Karolina, but also to create an ecosystem that would allow to use this computer from the other classical computers, from the other supercomputers, and also enhance this environment by the quantum computers that we have within the consortium. We don't start this on completely from scratch. We already have several proof of concepts. So there was already a first quantum job submitted from the LUMI computer to the quantum computer running at Chalmers. So we have some ideas about how this can be done, and we can build on the expertise that is already in the consortium. Regarding the new quantum computer that we want to deploy at the premises here at IT for Innovations, we are aiming at the computer with a star-shaped topology. So we are aiming at the quantum computer based on superconducting qubits connected into a star-shaped topology. The advantage of the star-shaped topology is that whenever we need to entangle and interact and make sure there is an interaction between the qubits, with many other topologies, you would need to do multiple of population exchanges. You would need to do a large number of swap operations. However, in star topology, it is very easy to see that any qubit can interact with any other qubit using basically at most 2 swap operations. And since swap operations take time, they have a limited fidelity, and they basically limit the number of useful computation one can do because they occupy the useful decoherence time. The swap topology, the star-shaped topology may bring the advantage of being able to execute relatively deep or deeper quantum algorithms, quantum circuits compared to what we would have normally. So these are preliminary values of this quantum computer. So we expect to have more than 20 qubits. We expect a star-shaped topology, and we expect basically this pretty standard relaxation and decoherence times that are typical for the superconducting qubit type of technology, quantum computer. What is probably most important is that there is the integration with the Karolina and with the quantum computing. I will go relatively fast through this. So we basically can recognize several paradigms here. There is an independent quantum computing where you just execute the quantum circuits on the quantum computer via a suitable user interface. This is basically what Qiskit by IBM is offering you today via their web interface. However, we recognize that most likely the important thing is to combine the quantum computing with a classical computing, where I have a classical computing job, and this classical computing job may have one or several quantum accelerated kernels in it. Well, the majority of the job can still be classical, but there may be moments or problems within the more complex problem that can be accelerated by a quantum computing. And this is what we are targeting. These two approaches can, of course, be combined into a more complicated workflow. They can be organized into a cyclic graph and then executed in a more complex workflow where these classical jobs can even be executed on a very different hardware that may be federated across Europe. So looking at this execution model, we basically, within the LUMI-Q consortium, propose the following approach, that having an HPC machine, the Karolina machine, you basically submit via the login node and through the batch scheduler a regular batch job, the way we are used to do in a quantum computer. This batch job may be to a great extent a classical job. However, it probably will contain at some point a kernel. By kernel, I mean a quantum circuit combined with pieces of classical code that need to be executed in a very low latency along with this kernel and along with the quantum circuit. And this portion can be offloaded. The programming model is very similar to what we use when we program the accelerated machines, when we program the GPU accelerators. So this can be offloaded to a dedicated scheduler and then scheduled onto a quantum computer, executed on the quantum computer, where there can be a tight cycle between the quantum classical loop, and then the results can be returned back asynchronously to the regular job. The idea is that we want to provide both quantum circuit kind of access as well as a pulse level access, because it looks like that large amounts of the interest in these early quantum computers is actually maybe not really the quantum computations, but these quantum computers can also serve as a devices in which you can create in a very controlled way a very well-defined quantum states, and then study the interactions between them. And this can be controlled via this pulse level API, which we also plan to open on the quantum computer. The advantage is that this mechanism is generic enough that this can be extended into a full environment. We can include the Karolina computer with the new LUMI-Q quantum computer, but we also have a plan to include the other classical computers within the consortium, and perhaps also extend this to also use to a number of additional quantum computers that we have in the consortium, to create a rich ecosystem in which our users will have access to quantum accelerating the hardware from multiple computers across the consortium. So what happens here? The status is that we have signed the hosting agreement to host the quantum computer. We have a consortium agreement among us to procure and operate this quantum computer. We have submitted a grant application to really realize this idea. However, as a common project, it's called the ETP4HPC integration project, and it includes actually all six hosting entities of the quantum of the Euro HPC quantum computers that were selected as hosting entities to procure and run quantum computers. And this consortium is led by Jansík. And we also have a running tender procedure right now for the quantum computers. So the LUMI quantum tender procedure for the LUMI-Q quantum computer is open already since 14th of February. Okay, this is just to mention that the Karolina system is on the computer room, and there is a lot of, this is some overview of storage. So the Karolina system has a file storage, very fast storage to a local scratch. And when it comes to data, then there is also a storage to a project. And in principle, we are also on the computer room have a large object storage, which may be operated by our partner organization, CESNET, which may be accessible to many of you. Yeah, I will finish more or less here. I will just mention that we have a self-service portal where you can control your project and see your consumption and set up set up your projects, add your colleagues to the projects and similar. You can provide as a feedback via this portal. We have a very detailed documentation. The documentation is Markdown based, and it's accessible via Git, so you can just browse it. However, if you are not happy with the documentation and you feel that this can be improved, and you know how to improve, you can easily download a copy of this documentation, modify it, and and just submit a merge request. So it's very easy to contribute to the documentation, and that's maybe one of the factors why it's relatively well developed. We of course provide also the open on-demand user environment, so you can actually use a graphical user environment pretty easily on our supercomputers. And we provide a number of dashboards where you can see the actual status of what's going on the Karolina, what kind of jobs are running, how the nodes are occupied, and so on. And if this is not good enough, we have a IT support team of specialists that will help you with setting up everything. And if you have more complicated questions, then they will take it further to our colleagues that will be able to help you. However, I need to make sure that that you understand that we prefer that you communicate with us via a request tracker. In this way, all your requests and all the communication is recorded and doesn't get lost and will be resolved in a due time. And the last thing I will conclude here, all of this can be complicated. However, we have a very rich training portfolio and provide a lot of efforts into the training. We organize something like 10 to 12 trainings a year. I have to say they are very very high profile trainings. But very often I have to say that the trainers are actually very often people who actually developed the individual methods or published significant works on these methods. So I really recommend the training that we offer. And here is just a promo on the training that was just yesterday. There was a training on fundamental quantum computing algorithms and their implementation in Qiskit. It was very, very popular training, and there is a new training upcoming, for example, for scientific visualization with Parabeam. So with that, I would like to thank you for your attention and accept your questions.
Thank you, Branislav. So now I will share my screen, if I can. No, it won't let me. Okay. So we already have. I'm fumbling with my sharing. We already have two questions actually. So the first one was fairly early in the presentation. Question from Björn Adamski. Switching CentOS 7 to Rocky Linux 8? Question mark.
Yes, that's correct.
So
no, I'm not sure now.
Branislav, you can see the questions in the chat.
Aim is to go to Rocky Linux. I see it, but I believe it will be Rocky Linux. I can't remember right now the number 8 point something. But yes, it will be either CentOS or Rocky. I don't remember right now. I have it in front of my eyes, but I can't really read the slide anymore. Yes, but it will be this kind of 8 line, and the aim is to go into a long-term support Rocky Linux, basically. The main motivation for us to switch the
then
operating
we
system.
have a question from yeah.
I just wanted to say that it's the CentOS 7.9 that we are running right now is getting too old, and it starts to happen that some of the dependencies for some of the more modern codes are difficult to fulfill. So it's and also there is also the end of support, so we need to switch. Okay, please go ahead.
Okay. Yeah. Then, sorry, Gabriela, can you copy the questions in the chat? So next question is from Charles Hirsch, and it's what is the quantum computer hardware? Is it European? But I'm not sure you can answer that because you just told us the tender was on.
No, it's public information. There is a tender that is going on in the procedure. So it's published, and you can read it. You can read it. All the constraints are public, so they are publicly available. what you can see there is that there is no restriction for the European hardware. It's not restricted to European hardware. However, a part of the evaluation criteria is the European added value. So the European added value is an advantage, but it's not a restriction. We will, of course, prefer the European hardware and we will prefer the European added value. So it is part of the evaluation, and there's an advantage and extra points for this. Yes, the presentation material is available, as was already mentioned.
Yes, it is available in the handout section. You can download it from this webinar. So next one is from Nicola Tonello. I didn't completely get what the cloud was and how it connects to your InfiniBand and the rest of your systems. Would you mind going through that again?
Yeah, I think we don't have time to go through details, but basically there is a cloud partition. It is densely integrated into the rest of the system, and it actually has the InfiniBand interconnects. However, it runs the OpenStack, and it is using InfiniBand. Well, it is basically using IP over IB, and also there is also an Ethernet network. So it is using all the available networks to basically carry the data that the OpenStack needs to carry, and with a proper and it's let's say it is using InfiniBand IP over IB to carry all the information it needs and to access the storages. The storage for this is partially organized in this object storage, partially in the project storage, and the data are actually carried over InfiniBand for performance. And also one can use the InfiniBand for IP over IB. I mean, it's to communicate between the virtual machines that you deploy in this cloud storage in this cloud environment.
Okay, then we have another question. Hi, from Martin Matheson. How can I find your success story references slide deck easily? And yeah, actually, I had a question about success stories. I know everybody is probably interested in what you do with the system. So, is there maybe some success stories available?
If you go to www.it4i.cz, and there is a lot of materials, including slides and presentations, and some of them may probably contain a success story that you are looking for. What you can also look at is that for every round of the allocation, we are running the open access allocations 3 times a year. We also publish the abstracts of all the projects that have been granted the allocation on the system. So from there you can also see what other people are doing on the computer, what the computer time was granted for. Because the success stories, they typically tend to focus on the results of the IT4 innovations, but there is a large number of very interesting results from our users as well. Some of them may be in presentations, some of them you can read in the abstracts.
And do you know if you have industrial users? I mean,
yes, we also have some. We also have industrial users. It's not a very large proportion. However, we have users that are renting the computer time. That's one category of users, and then we have users with whom we have a common research activities. That's another type of the users. For example, Common Horizon 2020 project. And there is also a contractual research users. These are basically users who ordered from the IT4 Innovations as an institute some topic to research and to provide the research, and sometimes they participate on the research, and this way they also get the access. Otherwise, we use the computer for the benefit of these users to execute the research that they ordered for the contractual research. So yes,
Okay.
we have
And
this
then,
kind of.
yes, okay. So I encourage everyone to visit this the IT4I website to find out about this. And then we have a remark from Charles here. That was about the quantum computer, and he says but it would be highly unacceptable not to favor the European quantum initiatives in this highly competitive domain.
Yes,
It's
and
a remark, yeah.
once again, we will favor them because there is in the evaluation criteria, there is the European added value is evaluated and it has its weight, and it can provide a competitive advantage. So it is favored. That's definitely true, but it's not closed for those who don't provide the European added value. So we are
Okay.
not excluding anyone. However, we favor the European.
Good. Thank you for this precision. Thank you very much, Branislav. I don't see any other question coming in, so I think we will close for now. I just wanted to announce that so today we were in the Czech Republic, and next time we will travel to Slovenia because our next webinar is about the Vega Euro HP system in Slovenia. So if you please go to our website and you will find more information and a link. So no questions. Oh yeah, there is one new question. Let me this. Oh no, it was just a thank you note. So thank you everyone. Thank you Branislav for presenting Karolina today. I'm sure it gave lots of ideas to our audience, and thanks to our audience, we have We had a lot of today. Thank you everyone, and I hope to talk to you again on the 12th of April about Vega.
Thank you very much. It was my pleasure. And goodbye.
Goodbye.
Goodbye.